brief note, not brief, but I got some notes for you today with some examples. And actually looking ahead, it almost looks like this is all of the notes going forward. So let's see if I do the notes today. Yeah. So the notes that I'm giving you right now, that's the rest of the notes for the next quiz. Right, next quiz will be next Wednesday. Okay? So what you have on the quiz next Wednesday is Dalton's law of partial pressure, which we talked about last week. You have mole fraction, you have temperature, and then the stuff we're talking about today. Actually, I have some time for tomorrow. Okay, never mind. I guess I'm not going to get through everything I thought today. That's good. And then next week, Monday and Tuesday will just be review days. Okay? So you'll have all the material when you walk out of here today, except for one example. And then we'll have a little bit of homework going over tomorrow. I won't be here on Friday. I got an assignment for you. Monday, go over homework. Tuesday, go over homework. You got a little quiz. Okay? All right, so let's first talk about temperature. Does anybody remember what you should remember about temperature?
Measure the average speed of the particles.
We've got half of it.
Oh, and size?
So what do we call the combination of speed and size?
Kinetic energy?
Yes. So this is directly proportional. I'll tell you this though. When I woke up this morning, I was like, I actually feel like a human being, and like, I was like so excited to like be like just feel normal and have to go to work. It was like actually a good feeling. You know what I'm saying? Yeah. You're like, oh, I'm glad that's over. And since you guys are all guys, and you can handle this, you know what my wife told me as parting wisdom when I left? I don't care if this is on video. She told me don't trust any farts. So that's good words of wisdom. Is that good advice? Can you go later today?
Yeah, I think it gets very.
Okay, and I'm sorry.
It's fine. No, it's
I
fine.
couldn't last. Okay. If it can't be today, can you tomorrow during class?
Okay.
So either or. Average, directly proportional to the average kinetic energy of the particles in matter. So we can say this mathematically like this: Ke average, that's average kinetic energy, is equal to 3 halves RT. So we're coming across R again. I guess, by the way, too, getting ahead of myself because my brain's still a little scrambled. Over here, did you notice in the homework it says copy KMT into notes, page 220? Okay. KMT stands for kinetic molecular theory. You'll see it's on page 220. There's 4 bullets for it. It says 0.1, 0.2. It's kind of like Dalton, remember? Right? So guess what? It's going to be on the test. Right? I'm just going to say state the main points of kinetic molecular theory. All right. So this is
What's RT stand for?
R is ideal gas constant. T is temperature. So this is average kinetic energy. Average kinetic energy. And it's measured in units of joules per mole, or joules per mole. 'Cause I don't think we've come across joules yet, have we? It's the first time. We'll get into joules a lot more. So this, R, now look at this. R is R, right? R is the ideal gas constant. But I can express constants in different units. Okay? So this R is not the 0.08206 liter atmosphere Kelvin mole. It is 8.31 joules per Kelvin mole. Okay, so now the thing to keep in mind about that is it's different units. And the reason is because the units before were liter atmosphere over Kelvin mole. So we've converted liter atmospheres into joules. Follow me? They're just units that relate to one another. Okay? So just make sure you pay attention. That's different units. And what do you suppose temperature has to be?
Kelvin.
Kelvin. It is Kelvin. Okay. So let's do an example of that. Example. Calculate the total kinetic energy. Calculate the total kinetic energy of 1 mole. 1 mole of a gas at 20 degrees C. So first of all, do you notice that this doesn't depend on what the gas is? Right? 3/2 RT has nothing to do with the idea of what the gas is. It just depends on how much gas there is. Right? So if we're talking about 1 mole, because this is going to calculate joules per mole.
Does this have to be, like, could it be a liquid or an aqueous solution?
Haha, good question. Right now, we're kind of confined to gases. Yep, we're confined to gases right now. Good point. Okay, so temperature, what do we got? We got 20 degrees C plus 273 or 293 K. Hello. Okay, so kinetic energy average. Kinetic energy average equals 3/2 RT, or kinetic energy average is equal to 3/2 times 8.31 joules per Kelvin mole. So again, notice the different units. Hey Garrett.
He's teaching, that's why.
Okay, times temperature to 93 K. And so this is going to be kinetic energy average. Comes out to be, so like Kelvins are going to cancel. You see this, Kelvin and Kelvin cancel. Comes out joules per mole. So this is going to be 3562 joules per mole times 1 mole. 3562 joules. Allowed. So the thing I caution you on is be careful. If you're not dealing with a whole mole, you know, you're going to multiply by whatever the value is. So if it's half a mole, it's half that. If it's 2 moles, it's twice it.
Why did we multiply by 1 mole?
Because it's for 1 mole of gas. Right here.
So if
So
it
that's
had been
been
3,
Yeah, so if there had been 3 moles, you'd have multiplied by 3 moles.
Okay.
Is that good?
What is a joule?
A joule is a measure of energy.
But like how much?
It's kilogram squared per kilogram times a meter squared per second squared. So it's a force over a distance over a time. Okay, but there's also some squaring factors in there too. And that's something you get into a lot in physics too. Yes, John.
is the kinetic energy average always going to be 3, 2?
3/2, yes. Yeah, that's just a constant in that equation.
What would you use like joules to measure?
Energy. The measure of energy. Yeah. We're going to use it a lot next chapter.
How come you only multiplied 8.1 joules over?
No, because I don't know what I'm doing. Still recovering. Was it 8.31?
Yeah.
Oh, you know what happened? I think it erased.
Uh,
Because the space was there. I think I must have done it by accident. Okay, now let's move on to the next one. Okay, now I'm going to geek out on you a little bit about stereos and stuff. Okay. All right, I'm all into stereos and speakers, and nowadays it's a little different, but one of the things that we always looked at when I was younger is power amplifiers and speakers, okay? And so what you want a speaker to do is, or an amplifier is given an input, put out a waveform. Make sense? You want to put out a waveform, so you put in a growing amplitude and then a decreasing amplitude, and the electronics are doing that. Now, the bigger the waveform, the louder it is. It's called intensity. Okay. Without getting into too much detail, this would be more like a bass sound. That'd be more like a treble sound. Okay. I'm not so interested in that right now. But the louder you turn up a stereo or a system or something like that, it gets the waveform bigger and bigger and bigger. But of course, you're going to come to a point where you saturate what the thing's able to do. So when we rate amplifiers, they rate them on like how many watts they can deliver. Have you seen that before? Okay. So let's say I have a thing that says it can deliver so many watts. As long as my waveform stays between those peak values now, to be clear, again, I'm going to geek out a little bit. If you buy a piece of crap kind of sound system, they're going to tell you peak power, okay? If you buy a really good one, they're going to tell you RMS power. And that's what we're going to talk about here in a second, is RMS, okay? But let's just say for peak right now. Let's say this is as loud as it can get on the positive end and as loud as it gets on the quiet end. As long as I stay under there, I get a faithful reproduction of the sound. But let's say I turn the volume up, and I want it to go higher than it really can. And I turn it back down. What happens is this top of the wave gets chopped off, and they call that clipping. You ever heard of that before? Music guys would know what I'm talking about, right? That's what clipping is. And what they call it clipping is because you're clipping off the top of the waveform. So what the speaker's trying to do is follow that waveform. So the speaker's trying to go in and out. So is the amplifier. It's trying to go in and out, in and out. But when you clip, you go, you get stuck there for a second. You see how it's like it's trying to travel and go further out, further out, further out. But then you can't go any further out, so it just stays there. And this is how you burn speakers up, because what you're doing is you're putting the maximum power through the wires that it can handle, and it's staying at that maximum power. In fact, I had a buddy who had a pair of Bose speakers back in college, and he turned them up so loud it drove me nuts. But he turned them so loud that you could actually see through the speakers, because they were like white kind of plasticky kind of cones, and then we glow red underneath, because he was melting the coils. That's really what he was doing. Eventually he did. All right. Now, that's just a little bit about clipping. Now, here's another thing. Now, if I want to say how much power a speaker or an amplifier puts out, I run into a problem. One of the problems is the result of it being a wave. So if I talk about this side, say, being positive, and this side being negative, when I add that all up, basically comes out to 0. You follow me? Because all the positives you cancel out by a negative. Okay? And again, if I want to know the real power that this thing can put out, I'm not so much more concerned about what it can do in a peak. Because how much music do you listen to has one just big peak, and then everything else is quiet? You know, most of it runs at a continuous level, right? You might get some peaks, some loud stuff. So instead of talking about peak power, we talk about RMS power. Thank you, sir. I get to see you all kinds of times today, huh?
Of course.
Gerald.
Range of motion.
Okay. So, what we can do is a mathematical transformation that gives us an idea of what it can do on average. So first of all, what we do is this. Imagine taking all the peaks, and instead of having this come down like this, let's say we just flip it over like this. And then this one would come up, and instead of this one coming down like this, we flip it over and go like this, just mathematically speaking. So I've flipped over these two peaks. Okay? Now, what we're going to take is something called an RMS calculation of this. RMS stands for root mean squared. Okay? So, first of all, if you square anything, what kind of number do you get? Positive. So by squaring, that's what we're doing, is we're positive, getting everything positive. Taking the root, what the root does is that if you might look at this and eyeball in the center and say, oh, okay, well, that's the center of that height to that height. But the problem is there's fewer stuff on this side than this side, right? Because this is narrower here and this is fatter here. So by taking the root, we're getting a value down in this area. And then by taking the mean, I'm averaging it. And so what I'm doing basically, it's a mathematical transformation that basically says, I'm going to take all this data and sum it up into an average that is something about the average of most of the particles in there. Or most of the power that we're talking about in an amplifier. So again, root mean squared is a good way to do that. So it's a mathematical transformation. So I don't know if that made sense to you, but that's something that I'd like to talk about. So this is a root mean squared velocity. Okay, so we call that mu RMS. And we can say a root mean squared is an averaging technique. Have you guys taken stats? No, that's something you come across in the stats course pretty often. A root mean squared is an averaging technique. Okay, now let's think about this in terms of not stereos, but in terms of particles. Remember we looked at that thing about kinetic molecular theory? I had that little demo up. We'll look at it again after you copy it into your notes about all the bouncing balls going all over the place. Remember this?
Yeah.
Okay. The problem is that, let's say one bouncy ball is moving in that direction, gas particle, and one's moving in that direction. Then that one's moving in a positive direction, that one's moving in a negative direction. If they're moving at the same speed, they cancel out and they make zero again. Just like these waves, that one would cancel that one out. So what we got to do is flip it over so we pretend that all the gases are moving in the same direction. Follow that? Because if we talk about positive and negative directions, then we get into positive and negative subtracting each other and there's problems. So we're going to do the same kind of technique to basically put them all on the same footing. The other thing, I don't know if you remember this, is that I showed you that, and I'll show you it again, but not today, is that gas particles, when they space out, they get that thing called the Boltzmann distribution. We have particles going real slow, some particles going real fast, but the bulk of them are in here. And so what we're going to do when we do our root mean squared is we're going to do again our square to get everything positive. We're going to get our root, because we squared them, we're going to undo the root and get back to about the size that it was. And then the mean, instead of getting something up in this area, we're going to get something down in this area. And we're going to figure out where the average particles are, how fast they're moving. So this calculation goes mu RMS, oops,
What's that called?
mu, just like micro. Mu RMS is equal to the square root of 3RT over capital M. You got all your appendages? They didn't take any from you or anything? Okay, that's good. Okay, now the thing to keep in mind here is this capital M, this is molar mass, and be very careful, in kilograms per mole. Okay, so it's different units, it's kilograms per mole. So those are kind of odd. So if it was 100 grams per mole, you'd say 0.1 kilograms per mole. And again, that has to go with, because R, we're using R in terms of kilograms. Let's do an example. Calculate the root mean squared velocity. Calculate the root mean squared velocity of HCl gas at 20 degrees C. So basically this would be, let's say in laboratory to take a cap off of HCl solution, and we've had the HCl solutions over there. How fast are those particles moving when they turn into gaseous state? And it's surprising the number that you get. All right, so first of all, let's say HCl, there's one of each. These weigh 1. These weigh 35. That's 1. That's 35. That's 36 grams per mole. But I don't want grams. I want kilograms. And so that comes out to be 0.036 kilograms per mole. We also need temperature, and they gave us 20 degrees C again, plus 273, that's going to be my 293. Okay. So I can go ahead and set this up now. URMS is equal to square root of 3RT over M. Mu RMS is equal to square root of 3 times R, 8.31 joules per Kelvin mole, times T, 293K, all divided by molar mass in kilograms per mole, 0.036 kilograms per mole. Okay. If you don't follow this, memorize. Okay. Let's see. Joule is equal to kilogram meter squared per second squared. And what we have for units is this. We have joules per Kelvin mole. We have Kelvin. And we have kilograms per mole. Everybody with me there? Those are all the units I have under there. So just underneath, Kelvin and Kelvin go away, mole and mole go away. So what I'm left with underneath here is joules per kilogram, or I'm left with kilogram meter squared per second squared all over kilogram. Kilograms cancel, and when you take the square root of each, you get meters per second. You don't need to follow that, but do you see that, how those units do work out? Okay, that's something that's going to be more useful for you when you get to physics. Now it's meters squared, but you can take square root.
That's actually pretty cool.
Isn't that neat? Yep. So it works out, but just think about it like this. It's a velocity, right? It's a velocity. Meters per second, does that sound like a speed?
Yeah.
Okay? All right, so just, if you need to memorize, just memorize. If you can understand that, you're ahead of the game for next year when physics or whenever you take physics. Okay. Mu RMS equals. So I'm going to take this and multiply it all together, and I get square root of 202,903. And we said the units at that point would probably be, let's see, what would be at that point? We'd be at meters squared per second squared, or mu RMS, is equal to 450 meters per second. Now, I don't know about you, 450 meters per second is pretty damn fast. Think about that, okay? How big is a football field?
100 meters?
Around 100 meters if you count the end zones, right? So this is about 4.5 football fields in 1 second. So how come if I go over there and I pull off the cap of an HCl bottle, why don't you just smell it instantly? Or why, if I open up a bottle of perfume, why don't you smell it instantly?
Because they're taking a real diverted path.
Yeah, it's something called a random walk. And a random walk is just like if you start out at this point, you're constantly being battered and moving around. In fact, I can't remember the exact numbers, but it's something like this. It's similar with photons being developed or being formed inside the sun. Okay, so let's say down in the core of the sun, okay, down where all the nuclear fusion is taking place. Say all of a sudden this light photon is emitted. It can take millions of years for that light photon traveling at the speed of light to get to the surface of the sun, because it's just doing this. It's bumping into things to change directions. But once it gets to the surface of the sun and is emitted from the surface of the sun, it takes 8 minutes to get here. Isn't that crazy? I mean, I think that's stuff, I love stuff like that. It just boggles my mind.
So if it was on like a straight path, would we see things more brightly? Because like all the light particles, like from that light, they're not all.
I don't know that we would see them more brightly because they're still being emitted at a rate consistent with what they're being produced at.
But they're not all reaching us at the same time, are they?
No, they're not all reaching us at the same time, but they wouldn't either otherwise. You know, they'd still be being emitted over time. I think the rate that they're being emitted from the sun is very close to the rate that they're being produced. That's my understanding. But it's a neat question, you know.
So like the light that we see, it's not coming straight to us, it's like...
No. Okay, so that's when this light gets to you, there's not much stuff that's interfering with it from the time it gets to you. The problem is that the sun is so dense, is that as soon as that photon tries to move, it's so dense that it's going to go into another atom, interact with that atom, and then go on. So it's because of the density.
Okay.
On the radio thing, how do you get temperature for this equation?
On the radio thing, how do you get
With the radio waves for RMS? Never mind.
Are you talking like glow, the background radiation?
No, on the radio, the stereo you were talking about,
Okay.
isn't there temperature that
No.
you have to plug into this equation?
Okay. For mu RMS, but not for. What I was just getting at here was the root mean squared velocity thing. Was the idea of what a root mean squared
Oh.
is? Yeah, not the temperature
Would you
part.
plug in something other than temperature?
Well, temperature's not relevant. What's relevant here is either voltage or watts. Okay. Time, intensity.
Makes sense.
Yeah. But the averaging technique of root mean squared is the same thing. You know, take the square, makes everything positive. Take the root, you eliminate the square, but everything's still positive. Take the mean, now you get the number towards the middle. So you take things that have positive and negative magnitudes and put them all in the same footing. And then I was going to give you that definition, but I don't think I want to. I think I want to take a break. That's enough for me. So how about, you want to call it quits there today? Okay. I got